maybe I'll just give an kind of a priming up what we were doing in the last time. Okay. Bye. Okay, so these were the four ways. So see, so the question that we are trying to address is how to impart what you call performance and stability to the control system. Stability, of course, by poles. You can check if the poles are on the left-hand plane or anything. Or if you are, if it is left to the, if it is on the left-hand plane, you are reasonably safe. But the next aspect, as I have mentioned, is what you call the performance. So performance is very important. Why? Because eventually you need to have a smooth ride. So you don't want any unnecessary things happening. There is some hiccups. You are not getting good product, so on and so forth. So we have, so in an overall control system, of course, we have the process available. You cannot touch because you have been hired to control the process. So you cannot go and tell your what you call employer saying that I would like to change the process. No, they'll say this is not your job. This has been designed by a or licensed by a technology company. You guys are here to make it work. Okay, so then as a process control engineer or scientist or whatsoever, you tend to address the problem of controlling something. So let's say if it is a distillation column controlling the temperature of the tray, okay, CSTR, outlet concentration, so on and so forth. You studied the process and you got a good understanding of the process. Okay, then what have you done is you started putting the instrumentation around it because now you understood that you need to control the temperature, so you need to have a measurement. What you have given with is just a system. Okay, so you bought, or rather you given bulk order for sensors into companies like ABB, Honeywell, etc. Okay, you specify this is the temperature range. I am going to buy it, and for 20 milliamp, 1 to 5 volt. Okay, so you bought it. Okay, you may not be able to do. You might even hire a junior engineer of instrumentation to fix it. So you have to insert this sensors and thermocouple into the plant. Okay, and he would give you the measurements. Okay, so now you would be ordering for controllers. So now your option is either you do a soft controller or a hard controller. Okay, whatever. So if you want to have a hard controller, you can buy it from again market. You buy bulk orders. If you need a soft controller, you would order for a DCS system. Companies like Kogawa, ABB, Honeywell would come up and give you the DCS system. Okay, so their DCS system is also dumb, right? It's like you would have to install everything. You will have to say this is the process, and you would fit in all the process schematic, everything inside. Okay, then you ordered I2P control valve and you made the control system ready, but it's still you made everything what you call offline. You did not put anything online. So now it's your turn. So now you would like to run it and show to your what you call boss or maybe your promoter saying that now guys, so see this is now working, my job is done. But first of all, it has to work properly because you have added a lot of things inside and it should not make any what you call detrimental effect. So you went ahead and checked the stability, so on and so forth, drawn the overall closed loop transfer function, fix the poles, okay, and make sure and did router analysis or even drawn root locus, and you got a clear understanding. Okay, if my poles go this side, this is the boundary in which you need to work. Done. Okay, then as a first cut, you started operating the plan. At least it is stable. Performance you look at later. So now what you have seen, okay, you have been you were asked to make a product concentration of 98% purity. okay, your overall control system is just giving you 95% purity, but there is no problem. Your overall control system is not crashing. It is working, but it's not giving you whatever you want. So now come to the second point for performance. You need to match the performance. Okay, and now you have started looking at the components one by one, what I could do. Process you cannot do because it's already there. Sensor you bought, there is nothing can be done on the sensor. Hardly it just do anything. It just measures something. I2P it just obeys what controller says. Control valve it just opens as I2P says. The only place you can do some fine tuning or some what you call hands-on is the controller. So then, okay, so then you have decided, okay, I can now go back and tune or design the controller properly, okay, and you started kind of brushing up your old PDC basics. So now you find out that okay, you have been taught at least 3 ways. Fourth, forget about it unless you are doing a very hi-fi business. Uh, you can tune the controller design by means of if you have a process model available, or if you don't have anything, you are ready to. So you have so you will tell to your promoter that okay, I will do some field experiments and get some data, and I will do this. Okay, and the third maybe if both of doesn't work, or you might do all the three and take the best bet out of it. So this is the way we are going to do, and now we are going to look at the process model based controller design. And lastly, and most importantly, I told this is the opening up game, which would be which may be a technology from 10 years or something, by means of directly interacting with the system, which essentially means that there is no control. So essentially means there is no rule. So see, whatever PI and PID is rule based. I am repetitively saying this is rule based controller. What is the rule? Okay, it is something proportional to error. Okay, something proportional to integral of error, something proportional to derivative of error. So this is a rule, right? It contains 3 components. First component of the rule is giving you some proportional push. Second is giving you some integral action to take off the offset, and the third is giving you some anticipatory action. So this is rule based, and this rule is a priori fixed. And this rule is of your assumption that adding these components might help you to control. So if you don't have anything out, so you don't have anything means what? Like you don't know what it works. You have been given a very black box kind of a system. So you would have to try out. You probably need to learn how the system reacts to a response. So basically, you don't have. Okay, so this is the condition where you don't have no model. Okay, and what you call a priori. So if there is no model, you may not. You can still do field experiments. So you are saying, but you have been denied. Don't do field experiments because it is too much of an expensive affair. So what you could do in this case, you may resort to AI based, like reinforcement learning based approach, which we are not going to learn. As I told, therein what you do, it's fully algorithmic. Okay, you need to artificially create somebody known as an agent. Agent is technically the controller. It is more of a fancy name. And environment, it is the connotation of RL. Okay, reinforcement learning. So on environment is your process. Technically, agent is the controller. So why this name? So CS people who have a general, what you call, generally they have a tendency to kind of make things fancy. So you put agent and environment, so on and so forth. Agent is your controller, but environment is your process. So you would, and you do agent is blank initially. He doesn't know anything because, and of course, agent is what? It's a soft algorithm. Because unless you interact with the system, you don't know what is happening. So agent would send something into the system, some action. It is your control action. Okay, but you are there to observe how the system reacts, and you are standing here. Okay, sorry. Okay. You're standing here. Huh? What is? And you know what agent has done. Okay, so if the agent is good, send something. Send, agent has sent some action. Okay, but it's essentially what? Open the wall, close the wall, some instruction, and it is open. Flow went inside. Something happened. Your set point, your process is reaching the steady set point. You say that okay, well done. You put a pat. I'll say I'm giving you a reward. Okay, so now what agent will learn? Okay, so I got some reward. I know now. So it's like agent is your faithful, obeying, what you call friend. So it's like you give chocolates. You given chocolates to the agent. So what agent will do? So agent will try to accumulate more chocolates. So agent would now try to send in based on this information. Agent would try to send in another action because it doesn't know anything, right? And you need to learn. So you would put a network, neural network, of course, and that is the brain of this agent. If you need to draw a neural net, okay, whatsoever. So this is the brain of the agent. So agent now, okay, got some idea. So agent now try to put in some more action, which is very similar to that, so that he would get any reward. So he might. So again, you put your second action. Your process is again getting close to the target. Okay, you're given one more reward. Very good. Do the same. Okay. So sometimes, see, this is sometimes again send an action. So A1, A2, A3. So he doesn't know. He is randomly sending it with some information inside that. When you send A3, it has started deviating from the desired set point. Okay, so now you would say, okay, no chocolate this time. You are going to get a penalty. Fine. Okay, so then agent is feared. So what he will do? So basically, these interactions would continue in such a way that this brain of this agent would learn the total. So you have given a lot of reward and penalty. No, reward is always, so reward is good thing. It is all positive. So let's say chocolates are always good. Okay, and penalty means you are giving something. You are not giving anything. Okay. So P1, you don't have P1 to Pn, maybe something, because it might not do penalty, it might not do always the wrong action. So penalty, I am assuming, so those numbers you forget about it, maybe M I'll put just to make sure that they are different. Now what you would do, this is the total wealth that the agent earned. So this is cumulative reward people will call. And your now based on this information, this your network, the brain of the agent would try to maximize this cumulative reward so that it would work very nicely. So as you really see, there is nothing over here. There is no controller. So controller is of course your agent. I'm saying there is no rule here. You see, no rule, and also no model also. This is like you have learned while walking, right? So when you are a child, how do you walk? You put your first step, it will fall. You will fall down for sure. Then you would understand that when you try to, it's better to walk close to the walls so that you can at least hold and stand. Okay, then you would learn okay how to keep your first step. So these are all your rewards. What is the penalty at that time you got? You have fall down, you got hurt badly. So you would really understood that this is the way I need to operate so that my goal is achieved. So the same way. So this is something possibly going to be the technology. Maybe 10. I don't know. Maybe in futuristic at least. People are trying in small system. Now coming back to our case. Huh? Okay, so now just give me a minute. So now, okay, so let me just give you what we are going to do now. Sorry about this. Okay, so now we are going to learn two approaches that is used for learning the control design based on process model. One is called DC or direct synthesis method. One is IMC, which is internal model control method. So that is what we are going to do maybe another 30 to 40 minutes from now. Any questions at the moment? Are we okay to move, go ahead?
Yes, sir.
Cool. So internal model control, sorry, the direct synthesis is basically, as I told, it is a model-based control strategy. So what you have to do, but as there is a caveat, so direct synthesis approach might not always give PID. Uh, may not always give you PID. It can sometimes it can be just a PI result because it is fully model based. You will come to know why I am saying this. Okay, so what we are going to do here, you do some analysis and you get some controller structure, let's say GC, and now kind of you would try to match it with the existing PID structure. Okay, so let's say, so what I'm trying to say is you do direct synthesis approach and you will get a controller structure. So now what you would do is you will just say, okay, you would equate it with one this and you figure out what is Kc, what is tau I and tau d. So while doing that exercise, you may find that there is no tau d term. It may possible, but sometimes it may be there also. So you design a controller and basically you're equating it as a, because see the only way in which you give this parameters through your PID, right? So you have your PID board or the controller hardware that you bought in, where you need to supply Kc and tau I and tau d. So whatever controller structure in transfer function domain, you tend to equate it with the PID form and get this values Kc and tau I and tau d. Eventually it is the same. Okay, so now what is the philosophy of direct synthesis? So direct synthesis is probably one of the simplest works based on the one of the simplest logic. So you know all this. I am not going to repeat this exercise. You know how to get the closed loop transfer function. So let's assume that you are going to do it for set point change. So there are two options, right? One is disturbance projection and set point change. Let's say you are doing it for the set point change. Okay. So what you really need is that overall closed loop transfer function that relate input to the output y by ysp. You know it is the product of all the forward paths on the numerator and 1 plus all the terms in the loop in the denominator. So that is what is written over here. So I am taking off from here. This is all known to you from the previous class. Okay, so now what you can do, I hope I'm audible, right? Is there an issue?
No, sir, no issues.
Perfect. So you can only do two things. Huh? In fact, you can only do one thing: play with the controller. So what you will do is you isolate the GC term, okay, and combine all them together. This all transfer function you can multiply and get a simple transfer function. So what you are going to do here, keep GC because this is something that you need to design, okay, and multiply other things, everything, JM, JC, JB, JP, everything, huh? And you make a placeholder transfer function G, which is this. So the simplified form of the transfer function is GC times G by 1 plus GC times G. Why are we doing this? Okay, because you know all of this, right? Because you bought your valve, and for this being a model based process, you might know what is GP to some extent. To some extent, sometimes you might don't even know. So forget about that. At least you are able to combine. Otherwise, let me also rephrase this. So all these terms, GC, GV, GP, GM, you cannot do anything. GV you bought the valve, process is already there, measurement you bought from the vendor, you cannot do anything. The only thing you can do is for the controller, let's isolate that guy. Okay, so now what is that we are going to do? So what is that we really need? We need to make y is equal to ysp, the simplest philosophy that you can do. Okay, so to make y is equal to ysp, what? This y by ysb become 1. So this guy become 1. Agreed? Okay, so we will come to that later. So now what we can do is, so we have GC y by ysp is equal to 1 plus GC into 1 GC times G by 1 plus GCG. So let's forget about the fact that, so now you can take GC to the left hand side, y by ysp as a single term to the right hand side, and isolate GC as a function of G and ysp. This is just numerical algebra. You can do, you take this guy on here, take LCM, take all rearrangement would give you a very interesting expression. GC is equal to 1 by G times 1 y by ysp. Uh, 1 by what do you call, sorry, that was a visit, so I had to just stop. Okay, 1 by G we know, which is the product of all of this. Y by ysp is something that we need. Okay, and G, so it is now very nice. So did you isolate? You isolated everything. So now comes the problem. You cannot use this equation 2 for controller design. Why? Because you don't know what is y by ysp a priori. Why that is? Because it is the closed loop transfer function. The y by ysp also include the gc term. So now it is like a catch 22 or chicken and egg, whatever you would like to. You wanted to get gc, so for which you have done this isolation business. Okay, but while isolated and you got some terms on the right hand side which contains a term y by ysp, which is again a some function of gc. So what we do, so what the people who design direct synthesis did is the following. Okay, so what they told, okay, so you don't require y by ysp as it is. You, what you really require is y by ysp desired. So what do you mean by y by ysp desired? So you're designing a controller, right? So what you really need is y by ysp is equal to 1. Agreed or not agreed?
Yes, sir.
But of course that is impossible. What do you mean by y by ysp is equal to 1? When you start, like magic, right? You start your, so say your process, so this is the set point, and you do some set pointing. Magically, y become ysp. This is essentially mean that y by ysp is equal to 1. This is impossible, and most importantly, if you put y by ysp is equal to 1, this equation 3 would turn to infinity. So don't do that. Please don't do that. What you could do is to take more reasonable options of y by ysp. Instead of putting y by ysp is equal to 1, why don't you choose 1 by tau c plus 1, which is like first order system? What do you, so if you choose y by ysp is equal to first order system, what would happen? So y as a function of ysp. So your process would tend to reach your ysp. This is your ysp, but not immediately, but after some time. Because this is the first order system. No? You will reach, but after some time. Okay, so first order system is a good choice, and you can tune your time constants in such a way that how fast you need to go, how slow you need to go, depending upon your constraint. It is a design problem. You are free to choose whatever you want. If you really need a fast response, choose your time constant appropriately. Okay. So that is one option. So you may substitute 1 by tau c plus the 1. So see, this tau c s is very important. So I am not putting 1 by tau. So this is tau c. Tau c is what you call as the closed loop time constant. This is something that you desire to obtain, not the process time constant. It may be very different. This is my desire. I really want my system to behave to reach y by ysp in this particular fashion. Okay, and if you don't know g properly, you can put g tilde, and you can so what is g tilde? Is an approximate value of all of this, because you are multiplying gp here, right? So technically you won't get gp exactly. It would be an approximate value, because how do you get gp? Either somebody should tell you, otherwise what you do step test, or you would do something else and fix. You have, what it calls the process reaction curve, take the slope, calculate everything, you will get gp, but that will not be, as you always know, this is not going to be the true gp. So it is an approximate gp. As a result, so this g is also not fully computable, but you will get an approximate value of g, which is called g tilde. Okay, so now another case. So let's say your process, when you fitted your model and calculated your G tilde, and you got that there is a time delay term is also there, because G tilde contain a time delay term. So it is also good for you to take y by ysp as e raised to minus theta by tau c s plus 1. Why? It is the process time delay. Even if controller put your full efforts, it cannot be able to circumvent the inherent delay of the process. Okay, so it's like this, right? So let's say you wanted to, so you, let's say you go into the coffee vending machine. Okay, you put your cup and you press your what you call the press it for to kind of dispense coffee. There is some delay. Even if you press hard, it would only come after some time. So your action will not yield the reaction as it is. There is some time delay involved. You have to take it in your mind and take a better what you call a cognizant what you call design, because your process is also contain theta. So my y by ysp is also contain a theta. Why? Because whatever you do, it would take some time, but eventually it will reach. Okay, so if you put e raised to minus theta as over there, this is going to be the overall GC side. And if you need, now you have learned too many things. So if you don't want, because eventually you may also would like to see whether the poles of GC, where it is lying, is my design is correct, whether it is lying in the left half plane, or so on and so forth. What you could do, you can still use a Taylor series approximation, so that you would have a polynomial in the denominator. It is always good to have a polynomial in the denominator, such because you can check where the poles are placed, so that you are safe. Because see, you are doing to you are designing a controller maybe for a plant that is cost that has the value of million. So why, so you would be at that most what you call, so you will have to meticulously plan everything. So forget about the plan. Let's say you have been hired in Boeing or even Airbus to design controller. By the way, almost all the aircraft, they also use this PPI, PID controllers. Simpler, right? Everything. So so we are, and always, as I told, this has no bearing on our domain. So since we are learning for the process, we are applying it. This is like what you call simply translatable to any area. It can be mechatronics, it can be robotics, huh? It can be aerospace. Only thing that they would change is your GP. Here the GP is of the process, there the GP is of that particular system. Otherwise, theory is pretty much intact. Okay. Okay. So now coming to this first point, why this method may not yield you PI and PID. So now let's look at this particular case. So this is for the first order system what we have just developed what you call a synthesis controller. Huh? So now GC. So this GC now, how do you implement this GC? This is a transfer function. But what you have in hand is a controller hardware board where you have to fix, you have to insert the value of Kc, tau I and tau D. So what you will do? So you will do what you would just compare this, the standard form with respect to this, and find what is Kc and what is tau I. And for first order plus time delay system, for in this particular case, you would see that there is no tau D. Your process would be of this particular. So you can check, right? Huh? So you can simply check and figure out the Kc will be of this particular structure and tau I is equal to tau for a particular tau. So you, what is tau? It is the, so again, I am asking you to look at that, asking you to doubly make your attention. There is TC is very different from, so don't get confused by the various level of TC. It is the desired closed loop time constant that you design. This is for your system you design, because this is what contains the overall dynamics. Okay. And the second one is tau I. You know what it is, and tau is the process time constant. So don't get mixed up anywhere. So okay, so what I am trying to say, if you again, it's for you to check. You can equate this. You have also done, I think, as part of a tutorial problem, or in, if you have a structure, you compare it with the typical first order system. And sorry, the controller transfer function, and identify what is Kc and what is tau I. Okay, so now your process G tilde is second order, because there is also a possibility that by identifying it happened to be a second order. So in that case, you would see that all the Kc and tau I and tau D terms are there. Again, how to do it? Substitute here, equate with this term and identify what is the value corresponding to Kc, tau I and tau D. So you would see that in this particular case, there is, so whatever method you design, you won't get your PID form. It will only end it at PI form for first, because it is model based control strategy. If your model is first order plus time delay, regardless of whatsoever, it would end in PI controller. For second order system or more higher order, you might end up in PID structure, but you will have to write down and check. Okay. Before we go, I can stop if you have to kind of ask any questions if you have. Any issues, guys? All of you. Again, small crowd though. Ashutosh, Aman, Aranya, Devendra, Harshita, Hemant, Naveen, Samuel, Seema, Shivam, Shruti, and Vishruta. Is this okay? Anything that is require more clarity here?
Sir, overall process is second order, but Y by YSP we have assumed first order. Why?
Okay, so overall process could be anything, right? So Y by YSP is something that you want to reach your first order system to, or closed loop system to go. correct?
Yes, sir.
So it's like this, right? So okay, so now assembling a car, take an example. You put everything. Each of them are very different dynamics. So you put your tire, you put your accelerator, gearboxes. So they would have very, very different dynamics. But your intention is what? You need to travel from 0 to 100 kilometer in 3 seconds. So 0 to 100 in 0, 1, 2, 3 in 3 seconds in linearly. So this is you are dictating. Got it, no? And how are you able to do it? By means of this additional thing that you have inserted, which is the controller. It should be able to take up that. Agreed?
Yes, sir.
So why again? One more thing. Why do if you see and first order so why by YSP taking first? So okay, let me answer this question in the reverse fashion. So let's say you say that your overall transfer function has to be second order, and you decided that I will take my y by YSP to be second order. So what is the eventual result? It would behave the way you want. So this is our so let me just say case 2 and case 1, which is having the better performance.
Second one.
Absolutely. In fact, if I put here and if I put here second, otherwise it is the reverse. So you don't want a bumper. So performance is something that you dictate. Got it, no?
Yes,
Any
sir.
other issue? So you can, so if you look at your textbook, so they have very nicely given the, I hope they have given this IMC relation, so not IMC, direct synthesis relation for various uh, candidates of control, like various candidates of, let me check if they have given or not given. I hope they have given. It's not. No, I think they're not given. That's okay. They're given it for IMC. But what I am trying to say, let's say if you given a third order system, okay, you should be able to do this. The method is fairly straightforward. The only place where you require your intervention, see, if if I tell you, okay, what is the desired closed loop characteristics, okay, and the process model, you should be able to design a controller. This is straightforward because you only need to, and sometimes, okay, you may not be able to, so sometimes they would only give you, because let's say assume you are doing working in the field, they would give you the process, instead of process model, they will give you the step test experimental data. So what you have to do, you have to fit a model, take up that model over here, correct, and substitute, and closed loop time constant would be given to you because this is the performance dictator. Cool.
Yes, sir.
Okay, so now let's also look at one more key model based control strategy, a bit more complicated but better in terms of uh, so IMC is slightly okay, new in the sense it is 90s, huh? So it is how many, 30 years almost. So in the 90s to 2000 is where this IMC method was developed. It was developed by a person called as Manfred Morari, and is, of course, he's a faculty member, of course, interestingly a chemical engineer, huh? Manfred Morari, he is one of the what do you call final words in control, very very highly cited researcher. Just sorry about that. Okay. Okay, so Manfred Murray and his team of students, maybe I think 2-3 generations of their 1 or 2 generations of their students, they kind of matured this IMC based controller. I hope I am audible to you, isn't it?
Yes, sir, you are audible.
Perfect. Okay, so what IMs the Murari and their team told is the following. So they told, okay, it's always anyway, it's a model strategy, model based control strategy. So let's also put an internal model in the control of artificially. So this is the process model which you don't know, which is this is G tilde, which is the model which is developed from data or physics, you linearize or whatsoever, and you make the control loop slightly what you call cryptic. So what would happen in this case is really not, so you are having so your y minus y tilde is what is being sending back over here. So let's good or bad we'll come to know, but what is the idea here? I'll come to I'll see. So when you have a model which is so if you have a model inside the overall control loop, then you say that if the true model and the model output is very similar, you would only propagate YSP over here, and you keep this. So this is again in the control system design. So now coming back, how do we do it? So this is again a tricky loop. You see, this is why this is a tricky loop, because in the feedback loop you have got another comparator. So we have learned to solve these kind of problems in the tutorial last time. What to do in this particular case? So it's better to because and see, this is a comparator within inside the feedback loop, and you should get rid of it. So what you can do, instead of adding this over here, you can again put this as another level of control. This is exactly same thing that you have solved. Your I think the last Q1 is exactly same. So instead of GC, you would plant it over here and throw it like this. G tilde. Huh? Because technically there is no difference. Only one difference. This is minus, so you have to add plus over here. Minus to minus, it's going to be added as a plus. So that you have to do. So what would happen? So now it is like your control loop is having a feedback line inside. So the new control structure would be GC star 1 minus G tilde GC star. So this is also we know. So what Murari and co-workers told is the following. So you see, G tilde will be an approximate thing, because you would most likely determine it from the either from first principle or fitting from the data. And okay, so in this particular case, let's redevelop this closed loop transfer function. This closed loop transfer function is slightly different. Why? Because your GC, so it is like this. Okay, so This is your output. This is your YSP plus minus. Okay, this is your G, and so this is our GC. GC is a single point representation of the complex model. So okay, so what your GC is now, so if you go back over here, you would see that your GC is GC star divided by 1 minus G tilde GC star, because so U tilde you taken back, GC star was the original controller. That based on this inclusion of GC, you combine them as a single controller. So now let us look at the overall transfer function. Let's look at just the YSP to Y. You can also compute a D if needed, if later. But let's look at the Y by YSP business now. So forward would be GC G by 1 plus GC G, right? Okay, so which essentially means GC times, which is GC star. GC is this now. GC star into 1 minus G tilde GC star. I hope my screen is visible to you, yes. Times G divided by 1 plus GC star by 1 minus G tilde GC star times G. Okay, so again, if you take LCM and so on and so forth, what would happen? You do the simplification. It would be very nicely boiling down to GC star times G. This all will go. So 1 minus GC star would be cancelled in both the denominators. It would be 1 minus G tilde. I'm sorry. 1 minus G tilde GC star plus GC star into G, which essentially means that GC star into G by 1 minus, you take GC star out, it would be G tilde minus G. So this is the overall transfer function. Here why? Here, okay. Sometimes it is very, very bumpy. Okay, so here it is your Y, this is YSP. So this is the overall transfer function. Again, it has got. Okay, so I am coming back to this, our business. So what would happen? Just give me a minute. It would take some time. So overall transfer function in this case is a function of, would be, this is just something that we have derived. Similarly, you can also do it for the disturbance term. Okay. So now what, look at the perfect model case, which essentially means that when you have your G is approximately equal to G tilde or very, very closely equal to G tilde, because you have done field experiments and you got very good data, and as a result, you marked G tilde is equal to G. Then what would remain? So this would go off, then this would go off. So eventually it would be Gc YSP into 1 minus Gc star G into T. Okay, so now what Murari and Coworker proposed is the following. Okay, so again, so G is equal to G tilde, so it is interchangeably used. So you would assume that this is G tilde. They are all the same. So what Murari and Coworker told that, see, the process would contain lot of garbage transfer functions. For instance, it may contain a time delay, it may contain right half plane 0 because it contains both numerator and denominator, right? So what they suggested, you split the model into two parts. A part that contains time delays and right half plane zeros, which is called as G plus, okay, and with the steady state gain equal to 1, which essentially means it would be so you have to keep the gain to be 1 and the remaining part. So what have we done? You have isolated the time delay and the right half plane zeros, which are the complex phenomena, and I am just taking 1 minus, only I am taking G tilde minus. And what he proposed that the controller structure is 1 by G tilde minus times F. F is like a filter. It is it's like another transfer function multiplier. Again, it could be 1 by tau CS plus 1. Generally, it is 1 by tau CS times R, but R is usually taken as 1. So eventually, your closed loop transfer function is again very similar to 1 by tau CS plus 1, but it is multiplied by G tilde inverse. Okay, so now what have we achieved by this? So when we take the inverse of the model, you have got rid of G plus. So so G plus would contain terms like right half 0 and what you call time delay. So when you do 1 by of that, they would what you call result in unstable poles and rate of plane 0. If you take an invert, so it would be more complex to handle. So you just kind of got rid of that. We only took out the terms that is more rational, which you can invert. So they have proved, it's a mathematical proof, by using this factorization and using G tilde minus for controller design, they found that that has better performance, physically realizable and stable. Okay, so now how to fix the tau c here? Here also there is your G tilde minus, your controller GC is 1 by G tilde minus times 1 by tau c, sorry, not 1 by tau c S plus 1 times R. So here also there is a tau c closed loop time constant. How to fix that? They have provided some guidance. So you can keep, if there is a time delay, you can keep tau c by theta greater than 0.8. That is one way. Or and tau c is greater than 0.1 times tau. This is that process time constant. Or they have given multiple options. One, you keep tau c between tau and theta, or you keep tau c as greater than theta, and so on and so forth. So they have provided all these options, and each of them has their merits and demerits. So you can, so whenever you design a controller, you can choose one of this based on the closed loop response that you obtain. And most widely used option is this. Tau c by theta is equal to 0.8 and tau c is greater than 0.1 tau. 0.1 tau. So considering that, so if you have a model and you, how do you, so again, so this is again in the form of GC, right? So you have to translate it into the PID form, Kc into 1 plus tau is plus tau cs, tau ds. So for various process transfer function, your textbook has given how to compute this Kc and tau I by factorizing. So you may use that, but there may be a new example wherein if that is the case, you can apply the same principle. Okay, what is the main principle? You have to split the process transfer function into two parts that contain two components, g plus that contains all right of plane zeros, exponential terms, and keep it aside. Use the term that contains that only rational terms and take the inverse and multiply with f. F could be any, f could be 1 by tau c s power r. R is usually taken to be 1 unless otherwise specified, otherwise it would be given to you. And how to get tau c, and they have given multiple options, and most widely option is option 1, or if you are solving it, you might find that this option 1 most likely would give reasonably good result. So with this, I will stop for today. So we have now covered two strategies for model-based control design, and in the next class, we will most likely look the methods that is based on field trials. So which are basically celebrated ZN, which is called Ziegler and Nichols tuning method, and CC, which is Cohen and Kuhn methods. So that is, and also there is also a Tyrus-Lubin method, I guess. Where is that? I think Tyrus and Lubin method. This is the latent tuning, which is called Tyrus and Lubin method. So we will look at these in the next class, and which would kind of complete our controller design aspect. So I am here if you have any quick question, otherwise we'll take up in the next class. It's already 11. I don't want to hold you, but if you have any quick question, I can respond.
Sir?
Yeah.
Sir, no, not actually related to the material, but this like audit has opened audit withdraw. So I was just wondering what is the audit criteria for the course?
30. So I think 30% is the institute previously used institute rule. No, I think now they have given us to decide. I suppose, is that true, Ashutosh?
Yes, sir.
Yes, sir.
D, like
Your
equivalent to D, right?
what? This course? This is a DC, sir. This is a department code.
No. I'm saying equivalent to D is the technical audit. This
Yeah,
thing,
yeah,
no?
yeah, yeah.
Yeah, I
Pass.
would keep the same.
Okay, sir.
Just
Thank you,
pass.
sir.
Sure, sir.
Okay, guys. So we will see you on Friday. Okay. Any issues? 11:1. I don't want to hold you guys. Okay. See you on Friday. Bye bye.
Thank you, sir.